This is the third of 3 webinars that introduce the MoSSEC Business Object Model. This webinar covers breakdowns in their structure, interfaces with connections and ports, and finally the business object models for optimization. It is assumed that the first and second webinars covering the basics and methods have already been followed. The aim of the 3 webinars is to introduce the range of objects in the business object model and how these objects are interlinked. Why is this understanding needed? It is for the MoSSEC-enabled capability owners to understand which objects they will use for the inputs and which for the outputs for their functionality. It's also for domain specialist capability owners to understand what objects exist and so can be exploited by their modelling and simulation tools. The webinars include extensive UML and SysML diagrams, so familiarity with these concepts would be an advantage. The webinars do not cover the justification for the business object model and also do not cover how to link the capabilities together with the MoSSEC services. This latter is covered in a subsequent webinar. After this brief introduction, this webinar will introduce breakdowns and components, interfaces and optimization before summarizing. First of all, a brief introduction and some background. The MoSSEC Business Object Model was developed under Crescendo. It provides the structure for a distributed dataset, and that is the subject of this webinar series. The Business Object Model also defines the web services which are used to expose the distributed dataset. The Business Object Model is built on the ISO standards for 10303-233, which is Systems Engineering, and 10303-239, which is Product Lifecycle Support. The Business Object Model is structured in packages. The webinar series is in 3 parts. The first is the basics, covering base objects, actors, study management, model management, requirements management and decision capture. The second webinar covers templates, methods and inputs and outputs and process management. And the third and final webinar covers breakdowns, which are used extensively in architectures, interfaces and optimization. The MoSSEC Business Object Model can be found on the ASD SSG website at this location. There are 3 sections to it. The UML model, which is an XMI file of the UML model, and the descriptive documentation, which will be covered by this webinar series, and the deployment guide as well. What you need to do is download the descriptive documentation, unzip it, and then open the index implementer.html in the browser. This is what the documentation looks like. Every time you see this book logo in this webinar, it will be referring to this documentation. The documentation has an introduction section at the beginning and then the main body of the documentation, which describes the business objects. This is followed by a section on the web services and finally a section which is direct linked to the HTML representation of the UML model. The documentation is navigated by clicking either on objects in diagrams or by objects in the tree. There are notes for all the classes and there are then more details for each of the classes. There are also notes on the properties for the classes and on relationships for those classes. Just a quick UML refresher. A class looks like this. The italics at the top show the inheritance of that class, and then it has the package name followed by the name of the class. The brown section at the top are the properties for that class, and the sort of greenish colour are the operations for that class. An interface has this interface text at the top. There are other types of objects such as abstract as well. There are several different types of relationships. The composite relationship, which is shown by a dark arrow, means that the object is part of the parent of that relationship. A shared association, which is the open arrow, means that that object can be shared by many different objects. A realization relationship is a dotted line, which basically means that this object can realize the one it is pointing to. There is a generalization relationship, which basically means that this object is a specialization of the thing it is pointing to. The relationships have names and they also have a multiplicity. In this case it's status and 1. This section introduces breakdowns and components. It was developed in Crescendo and is very close to AP239, the PLCS standard. It was not used in any demonstration, so it's expected to be refined extensively during TOICA, and in fact that is the case. Breakdowns are included in the UML model under breakdown management. This is the diagram that we'll be explaining in the next slides. This is a pictorial view of breakdowns. Breakdowns can be of many types. They can be functional, system, physical. They could be an industrial breakdown, thermal breakdown, etc. Many elements in a breakdown can have multiple representations. These can be all sorts of different types, for example models, key values, tools, methods, all associated with that particular element in a breakdown. There can also be links between breakdowns, so this could be allocation of a function to a system, or allocation of a function to a physical element, or allocation of a physical element to a particular part of an industrial plant, etc. Here we are looking at the top section of the breakdown diagram. A breakdown is a way to organize a collection of things. Breakdowns are versionable and identifiable, so can have names and descriptions. Breakdowns can have a type to define what sort of type they are for example, product, functional, zonal, etc. Note, requirements are not handled in breakdowns, or rather not handled in breakdown structures. They have relationships between them, for example, derived or composed relationships, and this was covered in the first webinar. Breakdowns are of something. In TOICA we have already expanded what this is possible to be types of objects, and also in AP 239 there is considerably more types of objects. A breakdown has elements, and a breakdown element only exists in the context of a breakdown, and it's a way of structuring things, and they don't represent anything in their own right. A breakdown element has a type. Usually this is the same type as the type of the breakdown, but it does not have to be, which will allow for hybrid breakdowns. A breakdown is structured using the breakdown element usage. This is identifiable, so it can have a name and a description. It can also be used as the subject for justification and assumptions. For example, I put this here because, or I assume we need one of these because. It can also realize interfaces, and because it's an object, it ensures consistent parent and child relationships. Breakdown elements can be realized by zero or many things, and this can be used to group the objects. The object model does not impose any rules on what these types should be for the different breakdown elements. It is expected that this will be imposed as business rules for the use of the objects. Most things can be realizations of breakdown elements, and this list shows some things that are excluded from that list. This slide shows a simplistic example of an aircraft product breakdown. The details of the names are not important, but what it is showing is that many product elements in a product breakdown, and it implies a multi-level structure, though the breakdown element usage objects are not shown on this diagram for clarity. This shows two breakdowns, and although not included on the diagram for clarity, they are of different types. The product is on the left and the functional is on the right. It includes the breakdown element usage objects to show the structure of the breakdowns. Also shown in dotted is the links between the elements where one element is realized by another. A component represents a logical piece of a complex product. For example, a physical component in an aircraft might be a fuselage, a wing or an engine, or a system component could be the fuel system or the electrical system. A breakdown element can be realized by a component. These components can have representations which can be model instances, for example a geometrical representation which would be a CAD model, or there could be a behavioural representation which would be an FE model. They also can be structured using the component assembly structure. As with breakdown element usage, these can be identifiable, so can have names and descriptions. They can also be subjects for justifications and assumptions, so I'm putting this here because, or we need this because. They can also realize interfaces, and because they are an object like this, they ensure consistent parent-child relationships. The usage itself can have its own representations, for example, the behaviour component in a particular usage. Now we will look at a multi-level example that was provided by SNECMA during the Crescendo project to explain components and interfaces during the next slides. This is covered extensively in the documentation under Interfaces and Components. So this is a top-level view of the example. It shows three components: the engine, the mount system and the pylon, and these have representations, FE behavioral representations of FE models. The example is then expanded to show a second level. The mount system has an engine pylon connecting rod with a beam representation model. There are two ball joints, and these are the two usages of the same ball joint socket component. The component has two representations. Each usage has a representation each. The example continues with axis and bolt components and their associated usages. Now we continue on with the same example into the interfaces section of this webinar. There is a section in the documentation under Interfaces and Components which covers this in much more detail. The main diagram we'll be looking at here is under Interface Management, and there's an Interface Management diagram. This will be explained in the next slides. The first thing to notice is that the interface is not an object in itself. Instead, it is made up of a connection and ports. This is to avoid the possibility of elements of an interface being deleted and not the interface itself, or vice versa. Continuing the example, this shows a connection between two ports, one on each of the engine and the pylon. The connection has a representation, which is the beam representation, and the two ports also have their own representations in the FE model. Looking at this in the business objects, both connection instance and port instance are identifiable, so they can have names and descriptions and can be also the subjects of justifications and assumptions. They can both have properties to define the interface, for example the rate or the amount of heat transferred across the connection, or the rate or amount of heat absorbed through the port, for example a heat sink property, or transmitted from the port, for example a heat source property. Both of these are program objects, so they can have approvals. A connection must have two relationships to the ports. These are to and from. There is no enforced direction implied by these names, but a business rule could be imposed if needed. A port itself could have many connections. A port is on something, and these are the possibilities of that the port can be on. A connection instance can be part of an associated model network. Continuing, the connection instance can have representations which are model instances. A port instance can also have representations. These can be model instances, or they can be accessible model instance constituents, i.e., for example, a node within an FE model. As seen previously, there are connections between the components. Connections can also be between component assembly usages of those components. The connection objects have spring representations, and the port objects can also have their own representations. This continues on until eventually the end component connects to the same port on the engine and the same port on the pylon. Now to look at more detail about port relationships. Initially, all that is known is that there is some connection between these two components, the engine and the pylon. As design decisions are made, for example, to use a mount system, new ports are added on the engine that connect to the mount system, and these are a derived relationship between the original port, which was just connected to the pylon, and the new port connected to the mount system. The relationships between the ports on the mount system and its subcomponents is then a delegation relationship that basically shows that you're delegating this port to the port on the bolt. Now we start looking at hierarchical port relationships. In this case we're using a USB example. The USB has hierarchical relationships to a USB information, USB power and USB spatial ports. An alternative example could be splitting of a heat transfer port into conduction, radiation and convection ports. Now to look at the UML diagram for port relationships. A port relationship points to two and only two ports. It's identifiable, so it can have a name and a description, and it's a program object, so it can have approvals. It also has a type which tells you what type of relationships. Again, this is external to the business object model, and some examples can be some delegation, derivation or hierarchy relationships. The descriptive documentation goes on to explain how using components, component assemblies and connections and ports with their representations can be used as like a recipe to make integration models. For example, a subcomponent has an FE model representation which has inside a node publication that is the port on that component. This is true for the other subcomponents. These ports, when connected, can be assembled into the parent component, and the connections show which node in the FE model it connects to which other node in the other models. Now we shall go on to interface types and how they are related to interface instances. The diagrams are mirrored horizontally across here to make it easier to understand. This diagram continues from the previous UML diagram we were looking at. The old objects we saw were on the bottom and the new objects are shown with yellow borders on the top. The interface connection type can be part of a collaborative modelling template, and an interface connection instance is an instance of the connection type. Similarly with port types and port instances. Port types can be related. Note that for port types they are only linked to breakdown elements and components, not to the usages which are for the instances. Continuing with the UML build-up, again we have new objects with borders in yellow. The interface connection type can have representations of the model type, and the port instance can have representations of model types and accessible model type constituents. Now we'll get on to the interface specifications. Using the earlier USB example, as you can see earlier, the properties can be added to connections and ports. An alternative is to use an interface specification. This is likely to be a document or a standard, for example the USB standard, or something that needs more than can just be covered with properties. So the USB has a specification. The specifications can inherit from other specifications. For example, there could be a USB specification for the spatial, for the power, and for other information specifications. Specification inheritance and port relationships can be used to derive requirements. This is the UML for interface specification. So an interface specification is a methodology object, so therefore can have documents which are the specification details for that specification. It is versionable and it can inherit from other specifications. So these are all objects can have interface specifications. Now follows 3 examples. These are intended to show different ways to define a connection, and the choice would depend on the business scenario. This example shows properties on the connection instances reflecting the definition on the connection type. This example shows properties on the representations of those connection instance. And the third example shows a document attached to the representation, and this, for example, could be a CSV file with boundary conditions or similar. The final section covers requirements with interfaces. As shown in the first webinar, requirements can be satisfied by something, and these things can be interface port instances, interface connection instances, and components. This is an example using business objects. It shows an interface early in the design cycle where it is not known how the engine is to be attached to the wing, just that it is attached and needs to transfer a certain amount of thrust. Each of these components should satisfy a requirement. The requirements are shown at the bottom with their relationships. So, for example, the port on the wing must receive a certain amount of thrust, and the port on the power plant will transmit that amount of thrust. And then there is tracing relationships, for example, to a requirement on the component itself to provide amount of thrust, and a requirement on the wing that should support the power plant. The verification of requirements is done using model instances. These are likely to be representations of the connection or the port of the component, though this is not enforced. The final section in this webinar is on optimization, and we'll be looking at optimization templates and their variables and optimization in a context, also touching briefly on correlation. There is a section in the documentation on the optimization which describes all the variables and some of their usage. This is the diagram we'll be walking through in this webinar. It can be found under the optimization extensions in the business object model, and will be explained in the next section. The D2X template is a container for the elements in the optimization definition. The template has one or more objectives. Some algorithms can handle multiple objectives, for example genetic algorithms, while others can only handle one. Therefore, the number of objectives should be suitable for the proposed algorithms. Constraints can always be used when only one objective is possible. The objective points to the key value type. This is the type of the key value instances that are to be measured in the iterations or experiments for a design of experiments type of optimization. The optimization objective can have a target value and a resolution type for that target. The type is an enumeration, so external to the business object model, but suggested values are delta, plus or minus, tolerance for target, or a percentage, i.e. within a percentage of that target. The directed action is what the optimization is to achieve with respect to that target. Again, this is an external enumeration, and suggested values are things like minimize, optimize, greater than, eliminate, etc. A constraint has all the same characteristics as an objective, except it is labelled as a constraint. Some of the directed actions may not be appropriate in these cases. So these can be used when the algorithms can only handle one objective. There are two types of variable. Design variables where the values are under the control of the engineer, for example the bleed air temperature or pressure, and there are external values where they are not under the engineer's control. From the object definition point of view, there is no difference between the two. A template must have at least one variable, and the variable points to the key value type, which is the type of the key value instance that will have its values set during the optimization. A variable points to a distribution object that is the definition of how it can be varied. This is covered on the next slides with examples. A variable can have an optimal start value, for example for a Newton-Raphson type of optimization. Now to look in more detail at distributions. There are two types of distribution. A parametric diagram. Here parameters and moments can be used to define a distribution. Or a non-parametric, where a distribution is defined by an associated document. Classifications can be used to declare whether this distribution is continuous, discrete, uniform, normal, etc. Now to look at some examples. The first one is a parametric continuous uniform example. In this case, it is defined by a simple range with upper and lower limits. Another example could be a normal distribution for a wind speed external variable. This is not shown. Then we can look at a parametric discrete uniform. For example, this could be a number of ribs, or it could be a simple range between limits within a step size. Then we can look at parametric discrete. This could be used for high, medium, low type distributions. And finally, there's a non-parametric discrete, which could be used from a file. For example, this could be actual measurements of wind speed. The final two objects in this template are observations. These are things that should be measured during an optimization but are not constraints. And constants. These are things which are preset values in the optimization. A template can optionally set an algorithm. Many optimization tools have built-in algorithms, so this would not be appropriate. However, it can be used to specify the type of algorithm that is suitable for the template and or the extent of testing that has been done with the template. An algorithm is a method, and the reasons for it being a method are listed here. However, additionally to the method characteristics, it can have property definitions, e.g. a genetic algorithm has properties for population size, mutation rates, etc. It has a type, and for the template values for the algorithm, these can be set as suitable values for the template. The template is in a context. Usually this will be within a collaborative modelling template, and it shows how the models and key value types in the collaborative modelling template could be optimized. This then goes on to become associative model networks for each iteration. A study can deploy an optimization template. These can be defined before any associative model networks are created and indicates what optimization is requested. Once the associative model network is created, it can point to the optimization template, i.e. this is what was used to create it, and it indicates what to set the input values to for that associative model network, and it also indicates which key values in the associative model network are the objectives, which constraints and which observations, etc. Finally, an optimization service can be specified. This actor is usually a tool, but it can also be an organization or a team when the iterations are manual. It is expected that this actor will control the launching and review of the iterations of the optimization. It may also control the generation of the model instance data and key values within each iteration, but this is not necessarily true, as it may be a multidisciplinary or a multi-company optimization. Assuming it's an iterative optimization, it's expected that this service will create the associative model networks for the first iteration and set the values for the variables, and then data for the models will be generated and the key values computed. The service will then analyze these results and decide is the next iteration needed, and creating that iteration and populating the variables, etc. Design of experiments type of optimization is expected that the service will decide how many experiments are needed and the values of the variables for these. It will then create the associative model networks for each of these experiments. Initially, this is set at the study level, indicating who or what is controlling the optimization. When the associative model network is created, it will point to that service that is controlling it from the optimization point of view. Finally, it's also possible to specify a service for a template. This indicates that the actor is capable of controlling the optimization iterations. Correlation is also covered, and it's not in this webinar, but you can find more detail in the documentation. It's also covered in the UML model and can be found in this location. So briefly, what was covered? We had a look at breakdowns and interfaces with some examples for each of those. Then we got on to optimizations, and included within optimizations some distributions. Things that have not been covered in this webinar are some minor extensions, such as simulations, which just adds additional properties to methods, geometry extensions, which cover coordinate spaces for model instances, decisions and argumentations, which are extensions of justifications, meetings, which extend activities, quality reports, which are extensions of model instances, and uncertainty management, which extends key value and model instances. Some of the areas that are major areas that have not been covered here are security and trust extensions, and these are very, very closely aligned to AP239. And finally, value modelling extensions. Thank you for your time.